Welcome to other mathematical models. So in the last video, we looked at a couple population models, and now we're going to look at some physics, looking at Newton's law of cooling. So essentially what's Newton's law of cooling? So Newton's law of cooling states that if you put in a warm object in a cool medium, so if you put a warm object in a cooler medium, then the rate of cooling is proportional to the difference in temperature at any given point in time. So the rate the object cools is proportional to the difference in temperature between the object and the medium. I need to give myself more space. One moment. So if we express this with a differential equation, essentially what we have is that our rate of change in temperature of our object, T prime, is equal to negative K. Right? The object is cooling, so we presume that we should have a negative constant out front, times the difference in temperature, so T minus Tm. So here we have T is equal to the T of lowercase t is the temperature of the object at time t. And Tm can be constant or can be a function of time as well, is the temperature of the medium. So it turns out, as long as our medium is essentially large enough, like a room and then a tiny object inside, that the temperature of the medium stays more or less constant. So if the temperature of the medium is constant, we wind up getting that T of T is equal to the temperature of the medium plus a temperature, initial temperature of the object minus the temperature of the medium times e to the negative kt. So essentially, we have the initial temperature difference times e to the negative kt, whatever that constant was, and then plus the temperature of the medium will give us what our temperature is. So this is the initial object temperature. Again, we will learn in chapter 2 how to solve, how to come up with this solution, not just be told this is what it is. And you can also do this with a more complicated situation of the temperature of the medium does change as the object changes, simply because heat has to remain constant, total heat. The other situation we're going to look at goes back to a little biology and extremely relevant in today's world. We're going to look at the spread of disease. So it's generally assumed that the rate of change in the number of infected people so the rate of change in the number of infected people is directly proportional to two things at the same time. So it's directly proportional to the number of people who are infected, right? Presuming that each person will spread the disease to, say, 2 people or 3 people. So it's directly proportional to the number of people already infected. And the number of people who remain to be infected. And so what we get then is this rate of change I prime is equal to some constant R. You've probably heard about this R, rate of infection per individual, as we have heard about the spread of COVID. And then this will be times the number of people infected. So if each person is expected to infect, say, 2 people, R would be 2. And then we multiply this by S minus I. So here, S is the total number of people that could possibly become infected. So this is the total number of people who could become infected. So some diseases only affect certain populations. Other times you have vaccines, which will hopefully prevent some people from getting sick. So that's just the total number of people who have the potential to become infected. And I is a function of time, is the people who have been infected. So this model looks very similar to that Verhulst model for population. And it turns out behaving essentially in the same way. So note this equation is similar to the Verhulst model. And so it kind of behaves in the same way. So we wind up getting essentially the same solution curves. And this time around, it's the susceptible people. So essentially, however many people start off as being infected, it grows more or less exponentially until it starts to level off. And then we're limited by how many people are susceptible to this disease. Now, technically, the differential equation would allow us to have solutions that start with more people infected than S, but that wouldn't really make sense. So whatever time we're starting with, our solutions will level off as they approach S. More people can't become infected than are susceptible to getting the disease. So again, this was just two more kind of basic mathematical models that you will see in the real world that are extremely relevant to the world today, that are modeled with differential equations.